Theorem 5.1, the perpendicular bisector theorem, starts with a point that is on the perpendicular bisector of a segment. So if we have a point on the perpendicular bisector, by definition of a perpendicular bisector, we know some things. If it's a perpendicular bisector, we know that these segments have to be perpendicular, which means that this angle has to be a right angle. So by definition, we have a right angle. And if it's a perpendicular bisector, this point has to be the midpoint of this segment, which means that these two segments are congruent. So by definition, this is true. The rest of the theorem states that this point will be equidistant from either endpoint. So if I draw in the distance from this point to the endpoint, this segment will be congruent to this segment. That's by the perpendicular bisector theorem. Now, the perpendicular bisector theorem says that any point on the perpendicular bisector is equidistant from the endpoint of either segment. So if I move this point down, these two segments are congruent. The converse of this starts with a point that is equidistant from two endpoints. If that point is equidistant from either endpoint, then it is on the perpendicular bisector. In the converse, we're starting with the point being equidistant and concluding that we have the perpendicular bisector. The angle bisector theorem starts with a point on the bisector of an angle. Well, if this is the bisector of an angle, by definition, these two angles will be congruent to each other. The theorem says that this point will be equidistant from either side of the angle. The question is, how do we measure distance from a point to a line? If we have a point, let's say point W, how do we measure the distance from a point to a line like line L? Well, in order to measure the distance, I'm going to have to start at this point and end up on the line. So I could go here, or here, or here, or here, or here. The distance between this point and this line is going to be the shortest distance. To get that shortest distance, I'm going to start at this point and go to my line and make a perpendicular segment. So to measure the distance from this point to this line, I need to come up with a perpendicular line that hits this point. So I want to draw in a segment that is perpendicular to this side and perpendicular to this side. So by the angle bisector theorem, this distance is going to be the same as this distance. The angle bisector theorem says any point on the bisector of an angle. So if I move this point to here, these two distances will be the same. Now be careful. A lot of students will try to draw in that line. This is not the distance between this point and this side. The distance has to be the segment that makes a right angle between the side and this segment. The converse of that theorem says that if we have a point that is equidistant from two sides of a angle, then that point is going to be on the angle bisector. We're starting with this point being equal distance and concluding that we have the angle bisector. Let's use those theorems. In problem number 1, we're given that ray AD bisects angle BAC. So by the definition of an angle bisector, angle BAD is going to be congruent to angle CAD. And point D is on the angle bisector. So by the angle bisector theorem, BD is going to be congruent to DC. So how do we use that to solve for x? Well, these two segments have to be congruent. 3x minus 4 has to equal 2x. Once they're equal to each other, then I can use algebra to solve for x. Combine my like terms by getting all my x's on one side of the equation, and undo what's happening to x. So x equals 4. We can check that answer by plugging 4 back in. 3 times 4 is 12, minus 4 is 8. So BD is 8 long. We can plug in 4 right here. 2 times 4 is 8, so CD is also 8. Plugging this number in for x is a great way to check your answer. In problem 2, segment PO is the perpendicular bisector of segment AB. By the definition of perpendicular bisector, we know that this angle has to be a right angle, and we know that AO is going to be congruent to BO. And if we look, P and M are both on the perpendicular bisector. So by the perpendicular bisector theorem, AP is going to be congruent to BP. And M is also on the perpendicular bisector, so AM is going to be congruent to MB. So how do we use that to solve for x, y, and z? Well, we need to set up some equations. AO has to be congruent to BO, so x has to equal 10. And AM is going to be congruent to BM, so y plus 3 has to equal 14. And AP has to equal BP. 2z has to equal z plus 11. Once I have my equation set up, then I can use algebra to solve for my variables. In the first equation, x is already solved for. It's 10 long. In my second equation, subtract 3 from both sides. Y equals 11. And in my third equation, subtract z from both sides. I end up with z equaling 11. If I look at my picture, AM and AP can't both be 11. AM is much shorter than AP. But I have to remember that these variables don't tell me how long each segment is. It tells me how long or how big my variable is. In order to figure out this length, I'm going to have to plug this back in. 11 plus 3 is 14. So AM would be 14 long, which lines up with MB. And if I plug 11 back in for Z, 2 times 11 is 22. And Z plus 11, 11 plus 11 is 22. So AM is shorter than AP, and it's shorter than AO, which is 10 long. I can plug my variables back in to check my answers to make sure that they line up. 10 and 10, 14 and 14, 22 and 22.